One of the ways we mentioned to solve the Schrödinger equation for cases where we cannot get an analytic solution, for example, the helium atom, which has one nucleus and two electrons, one of the ways to attack that kind of problem is perturbation theory. We're going to talk here about time-independent perturbation theory. There's also time-dependent, which can be talked about in a more advanced course, say Chem 451. And again, perturbation theory is general. You can use it to approximate solutions to differential equations. And for this case, the differential equations are the Schrödinger equation. All right, here's the general idea. You divide the Hamiltonian, that's the total Hamiltonian that you can solve, into two parts. One is a Hamiltonian whose solution is known. And then added on to that Hamiltonian is this perturbation Hamiltonian denoted by H prime. And what you do is insert this parameter lambda. And lambda, when lambda is 0, the Hamiltonian is the unperturbed system. And then when lambda goes to 1, then the Hamiltonian is the full system, the unperturbed plus the perturbation to the Hamiltonian. All right, so again, applying this to the Schrödinger equation, H0 is a Hamiltonian whose solutions you know or can be solved exactly. And then H prime is small additive term. This works, as we'll see, there's first, second, third order perturbation. If you want to stop at, say, first or second order perturbation, that implies that this perturbation Hamiltonian is actually small compared to that. All right, so let's go into the details of time-independent perturbation theory. Again, we start with the Schrödinger equation, H psi equal E psi, but now we don't know, we cannot write down an analytical solution, and we're using perturbation theory to approximate the solution. As we said, we'll approximate the Hamiltonian as an unperturbed Hamiltonian, plus we're going to add on to that a perturbation, and we're going to dial in that perturbation with this parameter lambda. If lambda is 0, you get the unperturbed, I should put a 0 here, unperturbed Hamiltonian. And then if lambda is 1, you get the full Hamiltonian with the perturbation. So lambda is our parameter that we're going to use to turn on the perturbation. Now, as we said, this will work if you know the solutions to the unperturbed Hamiltonian. Okay, so let's suppose we do. Let's say that the unperturbed Hamiltonian has eigenfunctions, say, u for a particular state n. That's equal to E for a particular state n times un. So this is known. These eigenfunctions and eigenvalues are known. And so now what are we going to do? Well, we're going to expand the, for a particular state n, we're going to expand the wave function that we want. Now, this is wave function first order perturbation theory as a Taylor series. So remember a Taylor series that goes I is equal to 0 to infinity. You probably never thought you'd see the Taylor series again, but here it is. Of the ith derivative of the wave function with respect to lambda. So we're going to expand in terms of lambda so we can turn it on or off. And we're going to expand this where we have lambda equals 0. That means that we're turning on the perturbation by including higher and higher terms in the Taylor series. And then this is lambda, we're going to expand around 0, so this would just be lambda raised to the ith power, all divided by I factorial. So there's a Taylor series expansion in that, and what we're going to do is to later on expand the energy also as a Taylor series expansion. Well, let's just do a few of these terms. When I is equal to 0, that's just the 0th term here. That's the wave function evaluated at lambda equals 0. That's when you have no perturbation. So the wave function with no perturbation will just be u of n. And that's for the 0th term. Now let's add another term here. Let's go I equal 1. So this would be how the wave function, the wave function for the total wave function, including the perturbation, with respect to lambda, evaluated lambda equals 0 times lambda. And let's do one more term. Let's do the second term, I equal 2. So this will be the second derivative of the wave function, the full wave function with respect to lambda. And now we evaluate this, lambda equals 0 times lambda squared divided by 2 plus and so on. Let's simplify the notation. Let's call this psi 1k or 1n. So this would be the term we have to add on to the unperturbed wave function in order to correct it. And this is lambda raised to the first, so this would be the first order term. And let's include this term here with the 2. We'll put the 2 in there. We'll call this 2n. So this is the second order, it's lambda squared, second order term that we have to add in to the wave function un that we know in order to correct the wave function second order, third order, and so on. So we can rewrite this. We're saying that the wave function of the whole system is the wave function of the, for a particular quantum state n, is the unperturbed, plus the perturbed system. I'll get rid of that comma there. I guess I'm not using that comma. Times lambda plus that second order correction to the wave function times lambda squared plus so on. All right, so let's do the same thing for energy. We're going to expand energy, the real energy, with the full system. It's going to be expanded as a Taylor series over I equal 0 to infinity. How the ith derivative of the energy, that particular quantum state, with respect to this expansion parameter, again evaluated at lambda equals 0. So we're starting at the point where there's no perturbation, times lambda raised to the I, this is lambda minus 0, we're expanding about 0, divided by I factorial. Let's write down a few of the terms. The I equals 0 term, this would be just the 0 energy. So you take the 0th derivative, you just get that term, and it's lambda equals 0, so it's the unperturbed energy of the end state, plus the first derivative of the energy with respect to lambda, evaluated lambda equals 0 times lambda. This must look familiar. The second derivative of the energy of the nth state with respect to lambda equals 0 times lambda squared plus and so on. And similarly to our notation before, let's call this E1n. So this is the correction, energy correction term you have to add to the unperturbed state for first order. We'll call this, there should be a 2 divided here, so we'll include the 2 in there. We'll call this as E2n. This is the second order correction to the energy, and so on. So we have lots of corrections here. So just rewriting this is the unperturbed energy plus a correction, first order correction to the energy, plus a second order correction to the energy, and so on. And this is for a particular quantum state given by the quantum number n. Now that we've expanded the energy and the wave functions in terms of a polynomial, or expanded in terms of lambda, and here I've forgotten the lambdas, so we'll just, so it's a lambda there, and then the second order correction to the energy has a lambda squared, and so on. Okay, now what we've done, just to review, is we've expanded our energy in terms of this turn on parameter lambda, goes from 0 to 1. And we've also expanded our wave function in terms of that same parameter. All right, so let's go back up here. Here's our Hamiltonian. And we're saying that we have wave function psi n and energies En for that, for a particular quantum state n. All right, so let's go ahead and write the Schrodinger equation. That is H plus, that's these unperturbed Hamiltonian plus this perturbation times psi for a particular quantum state n is E for that state n times psi n. All right, so let's go ahead and put in the expansions for psi n, that's this, and for E, that's this in there. So let's write that over here, h0 plus lambda h prime times psi. Psi was the unperturbed u0, we've given that the symbol u0 for a particular quantum state n, plus the first order correction to that wave function for quantum state n times lambda, plus the second order correction term for that quantum state times lambda squared. I might as well just keep going here, plus and so on, h psi equal E. We've expanded E, here it is, there. So that's zero order term for the energy, plus the first order correction term times lambda, plus the second order correction term to the energy times lambda squared, plus and so on. E and psi, this is the zeroth order. Getting a little messy here. If we keep these things straight, I think we can go. So that's the first order correction term to the wave function, and here's the second order correction to the wave function, and so on. There it is, h psi equal E psi expressed as a function of this lambda, which if it's 0, you got the unperturbed Hamiltonian, lambda goes to 1, you get the perturbed Hamiltonian. All right, so h psi equal E psi. Now what we want to do is to collect terms that have lambda raised to the zeroth order, raised to the first order, raised to the second order. So to do that, we multiply these things out, and it'll get a little messy, but once we collect terms, it'll be okay. So let's look at these. Lambda equals 0, so it'll be an h0, and that will not have lambda in it, so that's lambda raised to the 0th power. It's a zero order correction. Everything else, if we multiply these things through, will have a lambda. So we just have h0, u0. And let's look down here. We have e0. That all has lambda, so it just has u0. So our 0th order terms will be, so lambda raised to the 0, that will be h, the unperturbed Hamiltonian, u for a quantum state n. Okay, so let's start collecting terms here. That's that. And then this whole thing will equal, and the 0th order term, lambda 0, that is E, the 0 order energy, times that quantum state for that quantum state n. All right, let's collect terms in lambda the first. Okay, so this would be plus. Now let's get rid of that. That may not be in the most appropriate place. So let's see if we can terms lambda raised to the first power. Okay, so here is lambda raised to the first power multiplied by that. That'll be one term. And here's lambda raised to the first power multiplied by that. That'll be lambda to the first. And any other lambda will be lambda squared, lambda cubed, and so on. So it looks like we have two terms on the left-hand side of this equation. h0 psi 1n plus h prime psi 0n. Okay, so we have h prime u of 0n plus h0 psi of 1n. All right, that's lambda. Over on this side of the equation, let's see what things we have in lambda. All right, so we'll have a e0 psi 1, that'll be a lambda. And if we multiply this term by that term, that will just be a lambda. And I think that's all. So we just have those two terms. Okay, so that will be, this again, lambda to the first power. So this will be E0 for the nth quantum state times the wave function, the first order correction, plus the first order correction to the energy times the 0 order wave function. And then let's do, I don't know, you want to do lambda squared? That's second order? Well, Yeah, we might as well. Maybe one more set of terms here. So where do we get lambda squared? So we'll get a lambda squared, this term times that, and that term times that term will give you lambda squared. And on the right-hand side, it looks like, let's see, we have this is a lambda and this is a lambda. So we have that as a lambda squared. And here's a lambda squared, that times that, and then we'll have this times that. So it looks like we're going to have three terms on the right-hand side that have the coefficient lambda squared. So let's write down that. Here's a lambda squared. So those terms will be the first order correction to state 1, energy times the first order correction to the wave function, plus the second order correction for energy. I guess we're doing it opposite here. Dyslexic to n times the 0th order. So that will be u of n plus the first order correction times the first order correction for the wave number, and so on. So did we do this term? Yeah, well, I don't know. We did that term. Let's check it again. I guess we didn't write it down. So we get that and that and that and that. So the two terms on the left-hand side. So let's go ahead and do that. This will be the 0th order times the second order correction plus the perturbation times the first order correction. All right. That equals that. All right, you might notice like squared, you have like, that's a 2, 2, 0, 1, 1. Yeah, that looks, looks like I repeated this. So this should be, sorry, I guess I did that already. So this should be the 0th order for quantum state n times the second order correction. So 1 plus 1 is 2, 2 plus 0 is 2, 0 plus 2 is 0. I guess I don't use the, well, I should, but I don't. Okay. And this is 1, and that's 0. So looks like it's okay. And then plus there's a third order term and so on. And over here there's a third order term and so on. Okay, so this side equal that side. Now I've grouped them this way for that to be, for these two equations to be equal and for lambda to be any number going from 0 to 1. This means that the coefficients for lambda 0 have to be equal. The coefficients for lambda raised to the first power have to be equal. The coefficients for lambda raised to the second power have to be equal, and so on. Okay, so let's do the 0 order. Well, golly, look at this. H0 un is equal to E 0n un. Well, remember H0 is the unperturbed wave function. U is are the eigenfunctions for the unperturbed, and energy is the eigenfunction or the eigenvalue for the unperturbed. So this is nothing new. This is just H psi equal E psi for the unperturbed. We know exactly what this is because that was our supposition. We know what the eigenfunctions and eigenvalues of H0 is. So the 0th order, duh. I mean, we've said we know the solution to that already. Now let's look at the first order. And this is where we'll stop, first order. And this is called, the equation we're going to get is first order perturbation. So first order refers to this expansion parameter raised to the first power. Well, this says that H prime, the perturbation, operating on the original unperturbed wave function, and I guess we don't really use the 0 for that. So I guess we're just calling that un. Okay, un plus the unperturbed wave function operating on the first order correction to the wave function u1n. That is equal to the 0th order energy times the wave function operating on the first order correction plus the first order correction to the energy times the 0 order wave function. All right, so this is the basis on which we do first-order perturbation theory. All right, well, what do we want to do with this? Well, let's see. What we really want, if we go back up here a couple pages here, what we're doing is we're expanding the wave function for the whole Hamiltonian in terms of various corrections. So we start with the unperturbed, and we correct it here and correct it here. In the same way with the energy, we're starting with the unperturbed energy. We know what that is, and we add a correction, add another correction, and so on. So really what we want to do is to solve for the corrections. So what we want are the corrections. We want the first order correction to the energy and the first order correction to the wave function. Okay, if we know those, then we know we have a better estimate of the wave function energies, better estimate to first order. Okay, so how are we going to do that? Okay, so let's expand the first order correction for the wave function, psi1n, in terms of the basis set vectors that we know. So these are the vectors, these are the eigenfunctions of the unperturbed Hamiltonian, and these we know. And so let's sum over I, and we'll use a coefficient Cin. So we're expressing the perturbation to the wave function in terms of a linear combination of those wave functions we already know. All right, so with that, let's try to substitute in where psi1n is. So if we go here, that first term doesn't contain the first order correction, so we can just write that as h prime times un. Now that second term does contain it, so this would be h0 operating on here, but we're expanding it in terms of that, so it'll be the sum over I of Cin, again for the nth wave function, times ui. That is equal to, well, let's see here. There's psi1n. We're going to have to put that in. This is E0 for the nth state times the sum over I of this coefficient here. We're going to determine what that is. If we determine what that is, we know what the first order correction to the wave function is because we know what these are. So this would be ui. And then the last term here, that does not contain the first order correction, so this would just be the first order correction to the energy times the wave function un. So that's a fairly important equation. Actually, let's do a little simplification. So this is h prime un, nothing we can do there, but look, h0, we can put that inside the sum. C is a constant, so that can be pulled out. So we have h0 operating on ui. Well, that's just the energy of that eigenstate I times ui, because these are eigenfunctions of h0, and these are the eigenvalues. So this would be the 0, E0i. So we can rewrite this, I hope I've convinced you without too much trouble, of Cin times E, that's the zero order, this is for zero order, times ui. And I'll just rewrite these other terms here just to keep everything in. And this, by the way, would be for the ith wave function. This is just this term. I'm sorry, that's a u. We're expanding it in terms of it's a u. Wave functions we know, plus the first order correction to the wave function times that un. All right, so that's a fairly important equation, and we'll come back to this a couple times. All right. Now, what we want is, again, what we want is the first order correction to the wave function and the first order correction to energy. And how can we extract those things out? Well, the first order correction to the wave function, well, that will be equivalent to finding these coefficients, C1n. And once we know those, we just make this sum and we'll get that first order correction. And then somehow can we solve this equation to get the first order correction to the energy? All right, so what we want out of this equation is these things here, these coefficients C and the first order correction to energy. Well, what we can do is multiply both sides of this equation by for the nth quantum state, the complex conjugate and integrate over all space. So let's do that for each one of these terms. So let's go ahead and do that. Let me change notation. So for this first term, we're going to multiply by the complex conjugate of un, integrate over all space. Let's call that un h prime un. So this is the perturbation part of the Hamiltonian operating on the wave functions of the unperturbed Hamiltonian. All right, let's multiply by un star here. Un star, that means that if n is not equal to I, because u's are an orthonormal set, so unless n is equal to I or I is equal to n, the integration will be 0. So this will just be, we integrate over all space, we'll just have C n n. E is 0 for the nth state, and then when I is equal to n and integrate over space, since it's normalized, that'll be equal to 1. That is equal to, on this side, we do the same thing. The only thing that will come out here is when I is equal to n, otherwise it's 0, and when I is equal to n, the integration there will be 1. So this would just be E0n times C CNN, plus E1n, and again multiplying by un star integrating over space, it's an orthonormal set, so that's equal to 1. All right, so here's this equation. Oh, this is handy. These things cancel out. Oh, look at that. The first order correction to the energy is just this integral. Oh, that's handy. So the first order correction to the energy for the nth quantum state is just this integral. The wave function or the eigenfunction corresponding to the nth state, h prime un. All right, and that can be evaluated. We know what h prime is, and we know what the eigenfunctions are of the unperturbed Hamiltonian. You just do this integral, and that is the first order correction to the energy for the nth quantum state. Oh, we got it. And now, how about the corrections to the wave function? We got the corrections to the energy. Corrections to the wave function are equivalent to finding these values of these expansion coefficients Cin. How are we going to do that? Well, for that, let's take this equation, and instead of multiplying by un, complex conjugate, and integrating over all space, let's take a value, say j, not equal to n. So now what we're going to do is, this is an equation, let's call this equation 1. So we're going to take equation 1 and multiply by uj complex conjugate integrated over all space of equation 1. Okay, where j is not equal to n. Okay, so let's go ahead and do this. Let's multiply equation 1 on the left by the complex conjugate and integrate. All right, so for here we are, this equation 1. So we'll go ahead and do that. We'll change the notation there. So that term will be uj, perturbation operating on un. All right, so take the perturbation, operate on un. These are known. That's known. This is the perturbation Hamiltonian, which is known. So this integral can be calculated. And let's see what else we got here. We're going to multiply this term on the left with uj, where j is not equal to n. And it looks like when ui is or I is equal to j, that'll be that'll be plus 1. But when I is not equal to j, then it'll be orthogonal, and that will be 0. So the only terms, the only terms that will come out of here will be the ones where I equal j. Otherwise, this will make everything be equal to 0. So the only term that comes out of there is C, where I is equal to J. So that's Jn times E0I, where I is equal to J. So it'll be E0J. Okay, so we got that term on the right-hand side. Let's do it on the left-hand side. So we're going to integrate over, we're going to multiply both sides by EJ, and then integrate. That's a constant, comes out. The only terms that will come out of here is where I is equal to J. Otherwise, these terms will be 0. So this would be E0N times CJN. And let's do that last term there. All right, we're multiplying by EJ, where J is not equal to N. This term will go to 0, so because J can't be equal to N. So that term goes to 0. That's convenient, plus 0. Now look at this. We can solve for that coefficient CJN. So CJN will be the this integral UJ H prime UN divided by, so you put this over this side, so this would be E unperturbed Hamiltonian state N, unperturbed energy state N, minus E of J. So there it is. So here is the correction to the first order energy terms, and here's the correction for the wave function, first order wave function. So that's how it's probably pretty involved, and maybe you're half asleep by now, but I just want to show you the details, actually how you express the first order correction in terms of 0th order wave functions in a perturbation Hamiltonian for the energy, the first order corrections to the wave function as this integral. Again, it's 0 order wave functions with a first order perturbation here divided by these energies. Everything is known here, so you can calculate what the coefficients are for the wave function, and you know those, therefore you can describe that. So that's what first order perturbation theory is all about. Do we have this? Yes. For non-degenerate states, here it is, maybe in a little different notation from before. Now, why do we say non-degenerate states? Well, for example, if N and M, different quantum states, but nonetheless have the same energy, this term will be 0. So the coefficient in front of here will be infinite, and that won't make a very good wave function. So the assumption here is that wave functions are non-degenerate, and we made that assumption by making sure that J was not equal to N, non-degenerate wave functions. Okay. Now, maybe you're wondering about what are you going to do when you have degenerate wave functions? Well, what you're going to do is take Chem 451 and figure out how to do that. Okay, that's first order perturbation theory.